Thank you. Thanks. It's, I think, my fourth or fifth visit to China, and each time I get more and more impressed, not only by the hospitality of the Chinese hosts, but now also by this high level of activity, scientific activity in this area. And I'm really impressed by the collection of amazing people here in this conference, and I'm very thankful to be given the opportunity to give a talk here. So I'm going to give a talk about connections between quantum gravity and our universe. So quantum field theories, which describe how the particle interaction works, typically using Feynman diagrams to try to describe how the particle interactions take place, like some of these diagrams in this slide. We basically mastered it in many contexts, and in particular in experiments, in high-energy experiments like Large Hadron Collider. Everything we are getting seems to be consistent with the pictures we have using quantum field theories. So quantum field theory seems to be in good shape, but the quantum field theories that we typically are good with don't have gravity in them. So as soon as you put gravity, things get a little different. Naively, it seems not that different. You would just take quantum fields that you have, and you just add Einstein's geometrization of gravity, which means you have metric in the game, which means that the space and time have some dynamics itself. So you put the whole thing on a curved geometry, which is also dynamical, changing in shape and size and all that. And that seems to be all fine, and you might think that's it. So what is the big problem? The big problem is this approach does not work. Naively, it should have worked, but it doesn't quite work. In fact, the infinities that appear in Feynman diagrams are incurable. And so a conventional approach to quantizing gravity does not work. Feynman was the first to discover this, that quantum gravity is in trouble. So naively, the fact that the conventional approach to quantizing gravity does not work might have led one to say, even though Feynman did not say this, one may have said gravity cannot be coupled to quantum fields consistently and should always be viewed as a background field. It cannot be dynamical. Of course, that's not true in our universe because we do have a dynamical gravity. So therefore, there must be a different solution. So somehow, the fact that quantum mechanics and gravity are both existent in our universe and naively seem to be inconsistent with the particle physics interpretation of gravity seems to be in trouble. So the microscopic world, dominated by quantum world and so on, is in conflict with the macroscopic world that we have in Einstein's theory describing things like the scale of galaxy or the universe. So the UV and IR kind of don't match with each other in the context of quantum theory. So what we have learned is a way to solve the problem in the context of string theory, which is replacing point particles by strings, vibrating strings, or perhaps membranes or higher dimensional objects. So this has been a solution in the context of string theory to what the problem that Feynman had. So in particular, the way we think about this in the context of string theory is that we say that the diagrams that Feynman was describing should be fattened up to diagrams which involve replacing word lines with word sheets, and diagrams which he used to have to describe these kind of amplitude with what we called word sheets diagrams. So things seem to be just a minor extension of what we usually do in quantum field theory, just replacing point particle but by extended objects, that's all. Actually, this is not quite the end of the story, as it turns out, because it raises the following question: can we get every consistent quantum field theory in four-dimensional space-time coupled to gravity in a consistent way? In other words, the computation that Feynman was trying to do, does that work finally or not? Well, so string theory comes with extra dimensions. So typically we have 6 extra dimensions, and these should be viewed as compact, tiny spaces which have thus far avoided detection. And many solutions to what extra compact dimensions can look like exist. Popular class are, in fact, Calabi-Yau manifolds that Jan mentioned is one of the concrete examples that we have of how we can get potentially viable physics out of string theory. So this is a caricature of that. So at every point in extended space-time, we can imagine having some type of compact manifold, like a Calabi-Yau manifold, which is so small that we cannot detect them directly with large apparatus we have in experiments today. But of course, what we have, what kind of microscopic we have, will affect what kind of particles we see. So at each point over the space, we have some internal compact geometry here. I'm depicting it by a torus. And depending on how degrees of freedom, like strings or membranes, wrap around different cycles or how they are vibrating at a given point in space, we get different kinds of particles. So we have different manifestations of particles that we can get depending on what kind of geometries we pick. So different choices of compact space give you different kinds of observed theories. So one kind of a Calabi-Yau or one kind of manifold gives you one kind of physics with a particular gauge symmetry with a particular number of generations, another one with a different gauge symmetry with different matter, and so forth. The question is whether the right-hand side can become anything you want. Can you get any gauge theory with any matter field? Can you order the theory that you like and just say something on the left gives rise to it? That is the big question. So if indeed you can get everything on the right, you almost don't need to talk about the left. You just start with the right-hand side. And you would be just happy to say that there is some way to complete it, but you don't need to know the details if you're just interested in the infrared physics. Actually, it turns out that, and that is the big, I think what we have really learned in string theory, is that we cannot get arbitrary quantum field theories on the right-hand side. This is a lesson that you seldom hear, actually, in the context of string theory. I think that's probably, if I were to say what's the most important lesson we learned in string theory, is not only that quantum theory and gravity can fit into one framework, but you almost can get no quantum field theories that you like. That the only quantum field theories that you get are very, very special type. In fact, we believe we only get a finite number of quantum field theories from gravity. That is, in the short distance physics that you end up emerging, you only get so much limited theories that you get that's highly restricted. For example, if you take a maximum number of supersymmetries in 4 dimensions, what is called n equal to 4 supersymmetric theory, the whole theory is characterized by a choice of a gauge group. But in string theory, we always get the rank of this gauge group less than or equal to 23. For example, if you consider a gauge group SUM with m bigger than 23, this theory does not arise in string theory. So in other words, if you just choose a random group and you say, can this occur with n equal to 4 supergravity in 4 dimension, the answer is generically no. Only a finite set of them appear. So the number of allowed ones over all the possible ones is 0. The measure is 0. So the set of consistent quantum field theories that can be coupled to gravity are almost non-existent, very small set. So it appears that Feynman was almost right. That is, if you just chose a random quantum field theory, it just does not arise from a UV complete theory of gravity. So this raises 2 questions. Does the fact that most quantum field theories do not arise in string theory a deficiency of string theory or a general conclusion about consistent requirements for coupling to gravity? Evidence is emerging that this is not a deficiency of string theory, but subtle reasons for consistency of quantum gravity coupled to matter. And connections with basic facts of quantum gravity, such as unitarity and consistency of black holes, seem to indicate that. This has a lot of mathematical ramifications. For example, I mentioned to you that the typical compactifications that we use in string theory are Calabi-Yau manifolds. This picture, if you just get a finite number of possibilities, would predict that the number of Calabi-Yaus is finite. Indeed, this is something actually Yau had conjectured many decades ago from a mathematical perspective. So, and it's still not known if it's true or not, but this kind of picture that you only get a finite set of possibilities has this echo in mathematics. Now, what criteria distinguishes a good theory, a quantum field theory, which can be completed to a UV complete theory, from a bad quantum field theory, which means that you cannot complete it in a consistent theory of quantum gravity? It does not mean that quantum field theory by itself is bad. For example, n equals to 4 Yang-Mills with any gauge group is a good quantum field theory by itself. It's a finite theory. It's a conformal theory. So it's a beautiful theory. But if you ask the gravity to be part of the mix, you get into trouble for more essentially all gauge groups. So the swampland program is to try to say which ones are allowed, what are the rules of the game, which kind of theories can you get, what can't you get, how do you distinguish good ones from bad ones. Why is quantum gravity so strange? Why is it that we get such a weird thing that typically a lot of things that you think are fine suddenly are ending up to be bad theories? Part of the reason is that the powerful idea of quantum field theory, which without gravity is very powerful, is the notion of the effective field theory paradigm. This has proven to be tremendously powerful for both quantum field theory, particle physics, and condensed matter physics. The idea that short distance physics and long distance physics can be decoupled, that you can integrate out the short distance degrees of freedom and come up with an effective degree of freedom at large distance. Of course, that fact is true, but there's one more step that is not true. That is, the next step is that if you know what your symmetries are at large distance, you can come up essentially with what the theory can be, up to some finite number of parameters, which in principle can be picked depending on what is the short distance physics. This picture is false when it comes to gravity, that if you just give the symmetries and you just say, I want to write down the theory, go and write it down, typically it cannot exist without the complete UV psi. And that is where the effective field theory paradigm, so successful for particle physics and condensed matter physics, fails. And that is the real lesson we are learning in string theory. So this question is, how do we come up with the right notion of what is consistent, what is allowed with these restrictions? The main issue is what we call the mixing between short distance or ultraviolet degrees of freedom and long distance, the infrared degrees of freedom. They mix with each other. How does that work? Well, how do we measure short distance? How do we come up with short distance? In the context of particle physics, like in accelerator physics, we take two particles and shoot at each other, and the higher the energy is that the center of mass energy is, the shorter distances you can probe. So we take these particles and we shoot them at each other with ever higher and higher energies in order to figure out what is going on at shorter and shorter distances. That is the usual paradigm of particle physics and accelerator physics. Correct and very powerful. So we go at higher and higher energy. So if you take these particles, like two gravitons in principle, and shoot at each other with higher and higher energies, what is going to happen if you go to extreme high energies? Well, if you go to higher and higher energies, you will think that I'm going to be probing shorter and shorter distance. That is true until a certain energy. But if you go too high in energy, that paradigm fails. What happens is that when you go to higher and higher energy, instead of probing short distances, you begin to probe large distances, because what happens is that you begin to create a black hole. In other words, when you were thinking you're probing at short distances, suddenly there's this conspiracy that does not allow you to probe shorter than Planck length, and it becomes bigger instead of getting smaller. So higher and higher energies get related to large distance physics. So high energy and large distance become related. That's a piece of physics which is inherently part of the mixing quantum theory with gravity. So this is the new part of the story, that the black hole physics affects how we think about the short and large distance physics. Now I switch gear. So this was some descriptions of some of the issues in the context of quantum theory and gravity. And now I come to our universe. So a while back, Dirac noticed that there is this hierarchy of these strange scales in physics, these strange numbers, the large numbers. A rewording of what Dirac would have said perhaps today would be something like this. We have these very strange scales in physics. If you write them in terms of fundamental units of physics, like Planck's scale, we have the smallest non-vanishing scale, which is the dark energy, which is about 10 to the minus 120 in Planck units. Very tiny number. The age of the universe now, inverted, is about 10 to the minus 60 in Planck units. In other words, the age of the universe itself is a very big number in Planck units. The neutrino mass, the smallest non-zero mass particle we know of, neutrinos, the scale of it is about 10 to the minus 30 Planck units. I'm here rounding off factors of 10 and 100 I'm not careful about, just want to give you the order of magnitudes. The next scale, the scale of particles that we know of, quarks, the electroweak scale, and so forth, they're roughly of the scale of GeV and so on, which is about 10 to the minus 20 in Planck units. And then there's another scale which is recently suggested by Large Hadron Collider, which is a scale in which the Higgs potential becomes unstable, which is 10 to the minus 10 in Planck units almost. So there are these hierarchy of these numbers which look like they are related to each other by power laws rather than by factors of constants. And so Dirac was wondering, what is the origin of these strange hierarchies in physics? Some of these, of course, at the time they didn't have, like the dark energy and so on, but some of them they did have. In some form, you can reformulate what he was saying in the language I'm saying it now. For example, what is the nature of dark matter? We know we have dark matter in our universe. What is the nature of it? Is it related to dark energy? One of the features of dark energy is the smallness of it. As I just showed, lambda is 10 to the minus 120 in Planck units. And one of the features of the dark matter is the fact that it's weakly interacting. These are prominent features. Is there any relation between them, that the dark matter is weakly interacting and dark energy is so small? Are these completely independent? From the perspective of particle physics, naively, there is no relation between these two facts. Dark energy is small because it just put a small constant in Einstein's equations, and particles, dark matter, whatever it's made of, is weak. That's it. There's no relation. The explanation of hierarchy in these strange numbers are among the most important open questions for theoretical physics. Can these large and small numbers be related to the requirement of consistency of quantum gravity? I was telling you that essentially no quantum field theory can arise from quantum gravity, or there are very few of them. That gives us a window of opportunity. That means things can be finely tuned, because otherwise they wouldn't exist. The fine tuning might be a requirement for consistency with quantum gravity. Since the list of possibly consistent theories are so special, this might be Not so strange after all. Perhaps we can explain these large numbers. In other words, the choice of the compactification of string theory leading to some specific kind of solutions might end up landing you at a very, very particular corner of what naively you thought was possible. So if the space of all naive quantum field theories that you might think is okay, this big green space here, the ones that can be coupled to gravity is a very small subset of it. They might appear in some very specific corner. It doesn't have to be equally distributed. And therefore, what appears fine-tuned from the perspective of this bigger space, it suddenly becomes natural from the viewpoint of consistency of quantum gravity. So all these mysterious fine-tunings and all that might be not that mysterious after all. So this is the basic program, is to figure out what are these requirements giving us these quantum field theories that are consistent. So some proposed requirements to be consistent, or to be in what we call in the landscape of string theory, are the following. That there should be no global symmetries in a quantum theory of gravity, something that Hiroshi and others have worked on, and it's an amazingly important field for us, important aspect of quantum gravity that does not have any global symmetries. But you might ask why? Why should there be no global symmetries? Another feature of quantum gravity is what I would call uniqueness of quantum gravity. Could you have two completely independent, consistent quantum theories of gravity? The statement is no. That if you have one consistent theory of gravity and yet another one, they are connected to each other by finite energy or finite action processes. That there is no obstruction to go from one to the other. The range of fields in the theory of gravity is finite. This follows for what we call the duality conjectures in string theory. Gravity is always the weakest force in any consistent theory of gravity. Again, something which is not obvious. This is what's called the weak gravity conjecture. And then there are strong restrictions on critical points when you have positive potential, like the dark energy in our universe suggests, because that's positive. So if you have a potential which is positive, that potential is highly restricted, and what kind of restrictions are you getting? These are related to what's called the de Sitter conjectures. These are some samples of some of the things we have learned in string theory in the context of this swampland program. There are many more, but I'm just summarizing some simple ones here that I will try to explain to you what is the origin of some of these ideas, at least in some relatively heuristic fashion. So I will first tell you some basic facts about black holes, which turn out to be important for this story. If you take a fixed charge and a fixed mass, then you get a solution to black hole. You can also have it spin, but let me ignore the spin for now. As long as the mass of the black hole is bigger than its charge, there is a black hole. In fact, you can even take the mass equal to the charge, and that is what is called the extremal black hole. So the mass of this fat black hole can be bigger than or equal to its charge. Once you solve the Einstein's equation, you find that there's a requirement for the mass to be bigger than or equal to its charge. Moreover, Bekenstein and Hawking showed that black holes have thermodynamic properties. Namely, if you take black holes and combine it with quantum theory, you find that the black hole has entropy, just like a thermodynamic system, which is proportional to the area of the horizon of the black hole. So these are the facts I'm going to use, and the fact that the black holes always evaporate, the only exception being supersymmetric ones. So generically, all the black holes, except for the supersymmetric ones, will decay away. So why aren't there any global symmetries in quantum gravity? Well, what does a global symmetry mean? Global symmetry means something that you would say has a charge, like electron, but no electrical field coming out of it. In other words, global charge, but there's no remnant of it in terms of fields that you can measure. So why there can't be anything like that in the context of quantum gravity? The reason is that if you had such a thing, like the electron without electrical field, and if you throw that in to the black hole like that, and then the black hole absorbs this charge, but from the outside, since there's no electrical field coming out, there's no difference between charge inside and not inside, because there's nothing coming out. There's no Gauss's law, which gives you electrical field coming out. And therefore, it's just an ordinary black hole with a little bigger mass. And then when the black hole evaporates, it gives out charges equally of one kind or the other, plus or minus, and therefore, at the end, you find no charge, net charge left over, and no net charge coming out because the evaporation process is symmetric, and therefore, the charge you threw in disappears, and therefore, you have no conservation of charge. So the global symmetries disappear just because black holes evaporate. What about the uniqueness of quantum gravity? Well, we think that there is only one quantum gravity, consistent quantum gravity allowed. Now, this is, you would say, what does that mean, really? If you write down a theory on a piece of paper and somehow it exists, and somebody writes on a different piece of paper, another theory of gravity, and that seems to be consistent too, the statement is that these two theories, there's a way to go from one to the other with a finite action process, that they are not decoupled, that you cannot say that this theory and that theory are two different universes. You can have a process taking one to the other with a finite action. So what that means in the context of string theory is that if you take a space and compactify it on some manifold, take the tiny space to be M, and somebody says, I don't like your space, I want a different Calabi-Yau manifold, I want the space N, the statement is that there is a way to go from one to the other with a finite action process in physics. In other words, you can gradually move from one to the other, even though the topology and everything about the two manifolds might be different. You can do this in a finite action process, which means, in principle, in a laboratory, you should be able to accomplish this. This is an extension of the no global symmetries, because if there was no way to go from one to the other, you can characterize these by some charges, cobordism classes, mathematicians call, and that will give you a global charge. But I just argued there's no global charge, namely you can take one manifold and throw it inside the black hole. So you can throw one Calabi-Yau in the black hole and then it disappears, and therefore there's the charge with it goes away. So that means that there is no way to distinguish which one you are in terms of an absolute quantum number like a charge. This is actually perhaps reassuring. So if you don't like the universe you live in principle, there should be a way to get to any other universe in a bubble in our universe. You can create, in principle, a bubble of a different Calabi-Yau which you might like more. At least in principle, this should be possible. There's no obstruction. There's no obstruction to creating anything of that type. So all the quantum gravities are connected. If you have a gauge theory, all of the gauge theory charges are allowed. So if you have a U1 gauge theory, all the charges are in the spectrum. So for example, you could have thought about Maxwell's theory without any electric charges. Is there a problem with that? Suppose you had no electrons, just electric and magnetic fields. The statement is that no, you cannot have that. If you have Maxwell's theory, there better be electrically charged and magnetically charged objects too. How do we know that? Well, because of gravity. It has to be there through black holes. Because, again, using black hole description, Einstein's equation you can solve, and you find that there are black hole solutions for big black holes of mass m and charge q. And therefore, that means that for a given mass and a given charge, there are some particles, and the degeneracy of them goes like exponential of the area over 4, according to Wittgenstein and Hawking. And therefore, if you take one black hole of charge q and collide it with another black hole of charge minus q minus 1, or the other way, q plus 1 and minus q, put them together, you get a black hole of charge 1. So you can create any charge you want. So therefore, all the charges appear. Again, this is a property of black holes. The finite range for fields. This is related to duality conjectures and what is called the distance conjecture. This has been one of the important discoveries in string theory, I would say, in the past 20, 30 years, is the discovery of duality symmetries. And what it translates to in this language is that if you have a field, a massless field, phi, characterizing your vacuum, and if you change the values for the scalar field, you'll always run into trouble if you take too large a field value. Namely, if you start with one description, when you take the value of the field to get bigger and bigger, if it gets as big as Planck units, then your description of the theory you started with should break down. You have to have a different description, what we call the dual description. And why is that? What happens there is that as you go on farther away from the center of where you were to a farther distance in field space, you end up getting a tower of light state whose mass goes exponentially down with distance. And this tower of states are weakly interacting and gives rise to the degrees of freedom that describes the dual version of that theory. So the statement is that if you want to stick with a given effective field theory, you only have to restrict to a finite range in field space. Otherwise, if you go too far, your description breaks down, always. This is a fact that we know of from string theory, but we do not have a fundamental description of it from quantum gravity. Why? It had to be there. So this is one of the facts that we still lack a deeper understanding of why is it that there are always duality symmetries in a quantum theory of gravity. But we believe it is a principle that we have learned from string theory, that whenever you take extreme values for fields, you better find a dual description. And that there is a tower of states which go exponentially down in distance in field space, for which triggers the degrees of freedom of the dual theory. In fact, there's a potential application of this distance conjecture because there is a parameter in our universe which is very small, cosmological constant. You see, you can also apply the notion of distance to the cosmological constant space itself, because the cosmological constant dictates the metric. And there's a distance space in the metric, the field space for metric. And if you compute that, it's as if the cosmological constant goes like exponential of a field. And so if you compute the distance, it goes logarithmically with the cosmological constant itself. And if you apply the distance conjecture, you learn that there should be a tower of states in our universe which scales like a power of the cosmological constant to some power of order 1. So if you take the principles we have learned in string theory and extrapolate to the case of the cosmological constant being positive, you are forced to the conclusion that there must be a dual description taking over in our universe. What is that dual description? What is that tower? So we are naturally now connecting to the real world question. In our universe, we have a small parameter, lambda. There must be a tower. What is that tower? And what does the tower signify? What is the dual description? Well, indeed, it can be argued using other observations that in our universe, that power, the exponent is 1/4, and the light tower, at least I will, even though I won't explain, the reasoning is that this gives you an exponent of the order of 1/4, with one of the dimensions that I was telling you about to be larger than the other ones, perhaps of the order of a micron or so. And this is what's called the dark dimension. So here, now I'm taking this string theory and taking it to its limit, namely assuming what we have learned in string theory is correctly learned, which is in this case is distance conjecture, and applying it to the real world. Now we are really hitting the experiment. Now we can be proven or disproven with this kind of extrapolation. Are we learning string theory correctly? Is our extrapolation correct? And if so, what is this tower about? Another thing is that we are learning gravity is the weakest force. Now, this is true in all the examples we know in string theory. It's also true in our universe. Gravity is the weakest force. So, for example, if you take two electrons or two particles which are charged with charge E, there's an electric repulsion going like E squared over R squared. That's the usual Coulomb force. And then there's a gravitational attraction which goes like M squared over R squared, which is M is the mass. In our universe, the elementary charged particles have always a stronger electric repulsion than gravitational attraction. In other words, in fundamental units, their mass is much less than their charge. So, for example, for the electron, the mass in the fundamental units is about 10 to the minus 23, and the charge is about 10 to the minus 1. Much, much smaller. So in this sense, the gravitational force between electrons is much smaller. The statement is that this is true in any conceivable universe, not just in our universe. Now, this is true in string theory, but what is the quantum gravity reasoning for it? Well, there's a black hole, heuristic black hole explanation of this, which goes like this. Start with an extremal black hole where the charged black hole satisfies charge equals to the mass. And if it's not supersymmetric, we expect this black hole to decay. And if it decays, what's going to happen? Well, you're going to emit elementary charged particles of small charge and mass. And by charge and mass conservation, the charge goes down, the mass goes down. But as I said, when the black hole, the fat black hole, is decreasing in size and charge, it still should satisfy that the leftover mass is bigger than or equal to leftover charge. In other words, the Q minus the small q that goes out should be smaller than the big mass minus the small mass that goes out. And if you start with Q equals to M, you learn that the mass is less than or equal to charge. So again, features of black holes suggest a motivation for this weak gravity conjecture, that there are elementary particles whose mass should be less than or equal to their charge. There is further evidence for this weak gravity conjecture. Pure Maxwell theory coupled to Einstein gravity leads to naked singularities in regions with strong E field. In other words, suppose we forget about what I just told you, and somebody says, I want to study Einstein's theory coupled just to a Maxwell theory with no charged particles. Then in certain cases, you find if the electrical field is strong enough, you get naked singularities. Namely, you start with no singularities, and then you evolve the theory, and you suddenly find that there are singularities that are not hidden behind the horizon. There's no proof that this cannot happen in a quantum gravity, but there are principles that suggest that perhaps this doesn't happen. For example, Penrose suggested that many years ago. In fact, without using that, weak gravity conjecture predicts this cannot happen for a different reason. First of all, the fact that pure Einstein theory cannot couple to Maxwell theory without charged particles means that there must be charged particles in this theory. It cannot be a pure Maxwell theory. Secondly, the weak gravity conjecture tells you that not only there are charged particles, their masses cannot be too big, that at least some of these elementary charged particles have mass less than their charge. And then when you take these two facts into account, when you try to find naked singularities in the previous example, you find that these charged particles get created, and they screen the electrical field, and they get rid of the naked singularity. So from a very completely different kind of motivation, you get solve a different problem. There's another application of the weak gravity conjecture, and that's to our universe. And we are in a situation where there's dark energy, and it's almost constant, at least it looks like it's almost constant, and it's positive. So I talked about the condition that you have evaporation of the black holes and what restriction it gives you on the mass. It turns out for de Sitter space, you can also consider big black holes. Big black holes that size almost as the size of the whole universe. And in that case, you get an opposite inequality for the mass. In other words, the weak gravity conjecture says that the mass is less than the charge. But if you take a fat black hole in the context of de Sitter, you find that the mass is bigger than the square root of the charge times lambda to the 1/4, where lambda is the dark energy. So if you apply this to our universe, you find that the mass of the electron is between 10 to the minus 1 to 10 to the minus 31 in fundamental units. And the mass of the electron is 10 to the minus 23 in fundamental units. The lower bound mass is basically the mass of neutrino scale. So this is basically telling you that the mass of the electron should lie between the Planck scale, roughly, and the neutrino scale, which is a correct fact of our universe. It is not a very sharp quantitative prediction, but it is a quantitative prediction nevertheless. Moreover, we get restrictions on critical points of theories with potentials which are positive. This is an important question for early cosmology. For example, does inflation really take place in our universe? Can you have a region where you have a flat potential for a long range in field space, where it maybe rolls down to a value of the potential where we have a small value of potential, which we now call the dark energy, perhaps? Now, this is very difficult for us to study in string theory. The tools that we are good at in the string theory context are good when we have supersymmetry or we are at weak coupling. Well, we can ask whether this can be realized at weak coupling. Can we go to regions where we can actually study this? Well, weak coupling, we can study this. In other words, if you go to weak coupling in the language I was telling you about in terms of the fields, means you go far towards the corners of the boundaries of the field space. And then you can study this question, and you find invariably when you study that, you always get exponentially falling potentials. Potentials which are positive exponentially fall down with the field's value, always, with the exponent that you can actually compute. In fact, you find the V always goes like e to the minus some constant times phi for large phi, and the slope in Planck units, V prime over V, is always bigger than or equal to square root of 2, a very specific number. This is actually what you find in all the string examples we can construct. And you can ask, why is this number? Why do we get square root of 2? And okay, so we cannot get something which looks like inflation in asymptotic field regions. But the question is, what happens inside? So far away in field space, you get something which is exponentially falling down, but maybe you can have something like a metastable solution. What is the problem with that? You could have something like metastable or unstable situation depending on where you are, or you can have maybe like anti-de Sitter space if it's negative. Without doing too much work, we are now seeing that no model of dark energy is stable. That is, if you are, let's say, here, you will at best be metastable. That means you will decay. It might take a long time if the potential barrier is high, but it will decay. So we don't expect to have an absolutely stable positive energy in string theory. Precisely because at the infinities, we always get exponentially falling potentials. And therefore, a positive value will always have a way to tunnel out. So that means you will never have a completely stable positive energy situation. Therefore, without any detailed constructions, we already predict that our universe is going to decay. Whether it's going to decay slowly or abruptly, this doesn't tell you, but it tells you that we should be in a situation where our universe has a finite lifetime. Now, I told you we know quite a bit about what happens for the potential at large distance in field space. But you might be wondering what's going to happen in the interior regions. Can we say anything about in the middle? Could you have a metastable vacuum? What are the properties there? Unfortunately, we don't know as much about there because, by definition, we don't have weak coupling. We don't have a perturbative way to assess them. And we don't have supersymmetric techniques to have a control over these regions. So we are on a limb to try to make predictions from what's going to happen inside. However, there's one idea that has been proposed that will give you a prediction if it's true, which has the following feature. The proposal is that if you have a situation where you have any kind of potential, it should never be a situation that short distances smaller than the Planck scale can get larger than the whole universe. In other words, you shouldn't be in a situation that smallest possible distances that are unphysical, smaller than Planck scale, could overtake the whole universe, become bigger than the whole universe, and exit the horizon. There is no physical proof why this cannot happen. So this is just a conjecture. But if you take this and see what consequence it has, you immediately find that the potentials that you get should fall exponentially with the square root of 2 that I was telling you about. In other words, it predicts that square root of 2 that we are seeing in string theory at infinite distance. It also tells you that if it's true, and if you do have a metastable de Sitter, its lifetime is not too long compared to the Hubble, and you find the bound on the potential age of the universe, which is of the order of the 2 trillion years. So this simple picture would propose that you actually not only have a finite lifetime for the universe, but not too far from the Hubble scale. Now, of course, there are a lot of experiments going on these days to measure whether dark energy is changing at all, or what is the story with that. DESI experiment is one particular one which came up with some preliminary results just a few months ago. It's still too preliminary, so we do not know, but it's extremely interesting, as you can see, potentially relating observational physics to some concrete questions that we see in the context of string theory. This also explains the why now problem. Why do we live now at the time where the dark energy has just taken over? In other words, the time scale of the universe is about 1 over square root of lambda, and that's about the age we are now today. Why is that? Whereas the universe could have lived much, much longer if it was a metastable event with a long lifetime. Well, if this says that if you're in a universe whose lifetime cannot be much more than Hubble, then the typical lifetime that you will measure in such a universe is the Hubble scale, like the measurements we have today. So a typical lifetime will be the lifetimes we are measuring. So the measurement of dark energy also signals the end of our universe in a sense. That is, the measurement of the dark energy is a signal that we are in a universe which is about to end. Sorry about that slightly gloomy perspective, but okay. These ideas also lead to trouble with inflation, because inflation typically wants a large region in field space and so forth. There are ways to get around it, so it's not quite a rigorous picture, but there is another feature of the inflation which is at odds with what we are seeing in string theory. We expect whenever you go to extreme parameters, you should get a dual description. One extreme region is going back in time to early universe. If you had a very large temperature, you expect a dual description. You don't expect the same physics taking over, continuing to work, just like the field space. So temperature is one of them, which behaves like a variable in your theory, and you expect to have a dual description. So it's much more natural to, instead of inflation, to have an emerging universe from a dual description. So now let me just, since I'm running out of time, let me just begin to conclude with the thing that I hinted at, which was the statement that the dark energy is so small, and if you take the distance or the duality conjecture, it actually unifies with the dark matter. So let me remind me what I was saying. I was saying that the dark energy is so small, and therefore the distance conjecture tells you it should be a dark tower. But then I didn't tell you what is this dark tower. You could ask me, why haven't I seen that dark tower in my universe? What is this? But then you also have another problem. There's dark matter. You ask, what is the dark matter? So you have two problems. One is, what is this tower? The second problem is, what is dark matter? And the problems typically cancel each other out pairwise. And this may be one of those exact situations, that the dark tower that we are talking about is the dark matter. So the natural statement would be that the smallness of dark energy and the existence of dark matter are correlated. And the dark matter being weakly interacting is exactly what we have in the dual descriptions. So we have to have a weakly interacting dark matter, which would be what we expect for the dark energy to be small. So this will predict that the dark matter cannot be directly detected because it's weakly interacting, because the dual description is gravitationally interacting. And in this, if you put this idea together, you get a beautiful description of the theory where the dark matter abundance seems very naturally linked in such a way that it agrees with what we see in our universe, and it explains the coincidence problem, which is why the dark matter and dark energy, when with the radiation and matter temperature equality happens very close to where the dark energy takes over. And so, in other words, both the dark matter and dark energy get related to existence of a fifth dimension scale of the scale of a micron. Now, in the context of string theory, you might ask, what is this extra dimension scale could look like? This actually is very natural for us in string theory. This is naturally related to a particular kinds of Calabi-Yau manifolds, which has been studied quite a bit in string theory, and in the context of things like Ojava-Witten constructions, where you get an interval connecting descriptions of what's called the heterotic string, E8 cross E8. So you have something which is what would appear in the language of heterotic string as strong coupling, where you have one large extra dimension playing that role. So you would have some story like this, where the extra dimension is like an interval, or something like an interval, with our universe to be a 3 plus 1 dimensional slice in it, the dark matter being a gravitons in this fifth dimension, which is created not because it was there to begin with, but it was because of the afterglow of Big Bang. In other words, the Big Bang, the same thing which created the Big Bang, will also create this gravitons propagating to the fifth dimension. And that gives us the right abundance of the dark matter. It also sheds light, potentially, on the Dirac's puzzle of the scales. In fact, all the scales that we see get pegged to the cosmological constant. You see, in this fifth dimensional gravitational picture, the Planck scale in 5 dimensions turns out to be the lambda to the 1/12th power, which is 10 to the minus 10. The QCD scale gets related to 2/12th power, which is 10 to the minus 20. The neutrino scale gets related to the same scale as the dark matter, as well as the axion mass scale of the QCD, which is about 10 to the minus 13 fundamental units. And the Hubble scale is down to the 1/2, which is 10 to the minus 60. And the dark energy itself, of course, is 10 to the minus 120. So let me conclude. Swampland conditions can lead to potentially observable consequences for particle physics and cosmology. Almost all quantum field theories are in swampland, which lead to a predictive setup, since they are so rare to find good theories. Fine-tuning, such as hierarchy problem, may end up having a totally different solution. We should not be looking for field theory explanations of hierarchy. And that has actually not worked anyhow. And that has been a path that particle physics has taken for many decades now with not much success. With severe restrictions on consistent quantum theories of gravity. These ideas suggest that there are strong restrictions on light matter, and moreover, the positive energy in the context of quantum gravity leads to instabilities. Distance conjecture, or duality conjecture, suggests a unification of the dark sector, where the dark energy and dark matter are unified into one concept. Namely, small dark energy gives you the light tower, which could be dark matter. And new ideas, such as dualities, are expected to play a key role in early universe. Thank you. 谢谢.
Okay, so thank you very much. No questions? Oh yes. Later on, there's a question by young people later on. Yeah.
Yeah, thank you very much, Professor Vafa. So you talked about the end of the possibility of the ending of our universe, and I'd like maybe you can explain a little bit more details. So is this ending just like a decay of vacuum or the phase transition in our anticipated early universe, or it's something more furious such that it will destroy the entire space and time? Thank you.
Well, I think first of all, the answer to your question is that we don't know. We expect it to be a decay of some sort. Now, whether it's gradual decay like rolling on a potential or abrupt decay like a metastable decay tunneling, we don't know. But we expect to be one or the other. So those are open questions. I don't think we have the answer to that question.
Shimi?
Okay. Actually, I get very much interested in your duality between the dark matter and the dark energy. But the question is, for dark matter, the pressure is positive or zero. We know that. For dark energy, pressure is negative.
Yes.
So I get confused on how you can do these two.
Yes. So just to make clear, when I said they are unified, I wasn't saying that there's one object. I said there's one concept that leads to both, namely, the existence of smallness of lambda predicts that there is dark matter. That's what I mean. Not that dark matter is dark energy. No, that's not what I'm saying. Indeed, as you say, dark energy has different properties than dark matter. But the ideas that link them together, connect them to one theoretical framework predicts both.
Okay, I see.
Yes.
Okay, very thanks for the good talk by the professor. So I have a question about the inflation and the string theory. I wondered if the string theory can provide a natural explanation for the inflation, since in the standard mode the scalar field is very real. So, and the Higgs inflation looks not very good candidate.
Yes.
So I wondered if the string theory can provide such a natural origin of the inflating field.
People have tried to construct reasonable models of inflation in string theory, and people are still debating whether they have succeeded. So indeed, it's very difficult to get inflation from string theory. That's at least the fair way to say it. However, the way I think might happen is in the context of string theory, we have learned that a dual description is very natural when you take extreme parameters. So let me think of it this way. Take our universe and think about going backwards in time instead of forwards. What's going to happen? Well, temperature is going to go up, up, up as we go back in time.
Oh, so
let me just continue. So think about temperature in the Euclidean thermal circle. So there's a circle here. When you take the temperature to be large, circle is different size, and then temperature becoming small is a different size. So small temperature, large circle, thermal circle. Large temperature, small circle. So that parameter suggests that there may be a dual description for that physics when you go to dual description. So from all we know in string theory, we expect something else taking over. Okay, that's a natural expectation from string theory. Now, the ideas such as inflation were proposed at a time where we did not know about duality symmetries of string theory. And so we were not even looking for that. We were looking for a unified framework for all fields and one patch of field space to describe everything. Because that seemed like a nice thing. You have a complete description with one Lagrangian. That was the motivation for inflation to describe these. However, in the context of string theory, this is a requirement. You should not have a single patch description of physics. You should expect a dual description. It is a feature, not a bug. We are expecting a dual description. So the answer to your question is that I would expect a dual description, which is not local, relative to our degrees of freedom. So all these issues that inflation is trying to solve, like horizon problem. Why is the temperature here and there are equal? That doesn't sound local. Yes, because the physics is not local of the emergent universe. In other words, what we are emerging from was not local. Our degrees of freedom are not the dominant degrees of freedom back then. We are non-local relative to that period. For example, T-duality or mirror symmetry is an example of it. The degrees of freedom on one universe is not local relative to the other one. So therefore, if the degrees of freedom are reshuffled from the other epoch to our epoch, there would be non-local. And they would be presumably homogeneous. So many of the properties that inflation is trying to solve will be solved in a very different way.
Yes, very thanks.
Cumrun, towards the end of your talk, you started talking about a micron size fifth dimension.
Yes.
Does that mean, do I understand that the rest of the Calabi-Young manifold is also micron size? Does that mean the experimentalists should start looking at new physics at the micron scale?
Well, there are two questions you asked. So first one, the answer to that is that doesn't mean that all directions are Planck scale. In fact, I was assuming that all the rest of them are Planck scale, roughly. So no. But the second question, the answer to your second question is yes. Indeed, experimentalists are looking for the micron scale physics. And I happen to be peripherally connected one of these experiments, which is happening in Vienna, to measure the inverse square law potential deviation for the inverse square law for Newton. 1 over r squared force law for shorter distance should become 1 over r cubed if you go sufficiently small, if it's one extra dimension. And so this deviation, strengthening of the Newton's force law at shorter distance of the order of when you get to a micron scale is measurable potentially. They have gone up to 30 micron already with no deviation from Newton's law. So we are expecting, we are not too far from observing a deviation, and they are trying to do this experiment. And at time scale is not decades, but within a decade.
Just going back to the inflation, and you said in your theory, and it's not preferred for inflation difficulties. The question is how can generate all of the initial conditions, scalar perturbation, especially for the primordial gravity waves.
So if you're talking
you
about,
have mentioned that not all quantum field theory are consistent. We know that the observable commutative with respect to the Hamiltonian may not be complete. It's possible to change the situation when we adopt these extra assumptions.
So I'm not sure which question, is this related to the question was asked, or I'm getting confused.
Okay,
here.
okay, I can repeat it.
No. There was a question already asked, I didn't answer.
I will go first, you can.
So there was a question here, which was about the gravity waves, if I remember correctly, and inflation.
Yeah.
Initial conditions of inflation.
Yeah, inflation.
So in this context, so if the thing is emerging. So you have to have a model of how this emergence works. We wrote a toy model for this based on Witten's topological gravity of how this could happen, for example. That's an idea. In that context, there were no gravity waves, for example. And the spectrum being infrared shift turned out to be related to an anomaly in the topological gravity theory.
So this toy model may provide us.
Sorry, just a second.
Please.
So therefore, there are ideas to explain the redshift for the spectrum, and it will predict that there is no tensor modes, for example. So these are some ideas that could have concrete predictions.
Yeah, let me just add one sentence. This means current experiment on the same B mode detection is much more important.
Yes.
Either
you find it or not. It's certainly very
out
interesting.
inflation.
Yes.
And confirm
yes.
your theory.
It will be very interesting.
Yeah. Thank you.
Yes.
So I have a question about the dark energy and dark matter duality. So basically, we know dark energy is a constant, and dark matter concentrate in the center of the galaxy. Does this have something to do with the duality, or?
Not per se. I think that is just matter. It's clumps. So that's that. That's all. There's nothing to the duality. The idea that the dark energy and dark matter arise together was related to duality, not where they clump or where they are.
last question. So, yes.
Yes, you mentioned that so all the quantum gravity are connected together. So I just wonder, for instance, let us take a type 2 superstring on Calabi-Yau threefold. Then you can have a different topology transitions, right? Topology changing process. So my question is, how do you, in principle, compute the cost of energy during the process? Whether you can compute that in string theory in principle or not?
Well, you can, in principle, imagine